Okay, perfect. So for today, we're gonna go through the exam, okay? I'm gonna focus on problem one and problem four mostly. Two and three are very straightforward. I'll mention it briefly, but I won't go into much detail about it. I'll talk about how you solve it though. So what I normally do, I make the exam, I do it myself. Based on that, I know what the time estimate is, and then I add most of the time when it's in class, I add like an hour or two, and that will be the final time limit. This time was 48 hours, and it was basically to make sure that people that work in the weekends they have Monday to do it, and those who work on through the day, like also online, they have the Sunday to do it. So everybody is pleased, and everybody gets equal opportunity to do it. So and then what I do is I go through the exam after I did it myself in the solutions. I see how many steps it took to basically solve it, and based on that, I give points. And I think I found problem four extremely easy. Because of that, it was not assigned a lot of points, and I think that helped a lot of students at the end because I think majority of the people I think was a worth 6 or 8 points, and I think six was the lowest points that you could get for a question, and this was only worth 6 points, and majority got like two points by somehow, some way, at least coming up with the one or two good equations. So you still got like almost 30% of the points by just filling out two equations and then basically messing up the rest. So a lot of you got basically lucky and got still points, which helped your exam. So with that said, actually let's start with problem four, since we are on that topic anyways. So we had this. Let me see. 1, 2, 3, 4, 5, 6, 7. 3, 6. Another one, 7. And then we had 4 across. This is our problem. This side is fixed. And this side we have two forces. We had a shear force, in this case called D, and a moment called M. So what I also said is, okay, well, you have basically these stiffeners, strainers, whatever you want to call it, they're booms. So basically, if you look from the side view picture, let's redraw this a bit closer to it. So D, M. So if this is a side view, let's look at the front view. What we'll see is that we have this basically. 2, 1, 2, 4, 5, 6, 7, 8, 1, 8, 7. So this one was not needed. Let me see. Yeah, okay, 6 panels, 7 booms. So that makes more sense. Okay, like we saw this. And this is basically not, and then if you put the force on it, the force will be like here, right? So what you can do is, this is just an open shear flow problem. So we know from our open shear flow is Sy, Ixx, yeah. So you can just solve this and you get your, let's call this numbers. I think this was 1, 2, 3, 4, 5, 6, and 7. So we get here all the shear flows. So we get Q76, if we start here, Q65, Q54, Q43, 32, and 21. So the shear force is given. The moment of inertia, of course, that's your standard moment of inertia of boom. So that's nothing else than the summation of By squared. And if you did that correctly, you see you get a number out of it, 2.24 10 to the minus, or 10 to the power of 8 millimeters to the power of 4. So we know this, and then of course we can substitute the 5600, so this was 5600 newtons. We can basically get a number out of here, and what we get is do it? No, I cannot do it. Okay, so let's see. So you get 5600 over 2.24 10 to the power 8, 10 to the power 8, a minus here multiplied. And in this case, here you start 0, so the first boom you cross is by. So let's see what the dimensions were. So these were all 200, right?
Right, and the transverse ones.
So this is 200. So if you look from the center point of view, and this was also 200. I think these were 400.
Oh yeah, the distance is 400.
So 400. But they don't matter. So here your y is actually, I think the booms were,
Yeah, the booms were all 200.
Yeah. so you multiply by the boom, so that's 200, and then you multiply y distance, and that's negative 600. And then you get your force out of it, and that will be, if you did it correctly, that will be 3 newtons per millimeter. So this one would be 3 newtons per millimeter. So at least this one. That's right here. So let's do say 3. And then you just propagate upwards. And that's it. So if you do it correctly, then with this one you get 5. And then the other one would be, this one would be 6. And then because it's symmetric, 4, 5, 4, 3, this is 6 as well. Because now you're at the center line, so this doesn't add anything to it. So it remains 6. This goes back to 5. This goes to 3.
But did it flow in a different direction this time? It's a positive distance. Like at negative 600, but Q21 would be positive 600. So it flowed the opposite direction?
No. So now this was a negative. So now we got positive, positive, positive.
Right.
And now basically they decrease again, right? So that's already taken into account that you multiplied here with a,
Right.
because you just added up. So the shear force Q76, so if you do 6.5, say Q65, that's minus SY IXX, summation of BY, of course, because this is your starting point, plus Q76. So once you get here, because you add this number to it, you decrease. So this part of it, so if you do now correctly, say, let's do 3.2. 3.2 is this, and this will be 4.3. So this part will be a negative Q. Yes, correct on that.
Right.
Because this is negative and this Y is positive. But because this one is still, say, 6, it just decreases to 5 and then to 3. Okay. So, and then the next question was, so now we have the shear flows. And basically when you have the shear flows, it means basically in this panel, because you have the equilibrium, so if you have shear flow like this going up, the second, because you have panel equilibrium, the shear flow must go into this direction. So this is all 3 Newton per millimeter. And then this is all 5. And I'm gonna just draw the lines vertically, so this gap. So this will be 6 going in this direction. This is 6 going in that direction, 5, and 3. And of course, because this panel must be in equilibrium with this panel, you have 3 on the rows, and then 5, and then 6. And then you get the result. The rest is symmetric, okay? So that's actually all the shear flow. It was basically nothing more than an equation, an open shear flow section. And that's the reason why I said hint, look at the front view and solve the shear flow problem. So the second thing is these booms, if you look at this panel between these two panels, of course there's no equilibrium. One is 5 shear flow and the other one 6. So there must be some forces in these booms acting the strainers. And how do we get the forces? Forces are nothing more than stress times, in this case we have to look at the stresses as well. Stress times area. So in the stress we get by saying the moment times y over Ixx. And now we use the moment to determine the stresses in each of these booms. And once we have the stresses in the booms, we multiply by the area that was given, that was 200 millimeters squared, and we get the force P. So if you do the stresses in the booms, let's calculate again. This is actually used a different column. And we can calculate the stresses. In this case, let's say again, that will be 4.48 10 to the power 6, that was the moment, divided by 2.24 10 to the power 8. And then if we look at the top one, will be multiplied by 600. That gives us 12. And then we can repeat the same thing, multiply by 400, multiply by 200, and then we get negative 200, multiply by negative 200, multiply by negative 400, and multiply by negative 600. And then we get all the stresses, and they will be ranging from 12 to 8 to 4, and then this will be symmetric but then negative. So this will be negative 4, this will be negative 8, and this will be negative 12. So here we have the stresses. So now we have the stresses. So we actually, and then like we said, the force is nothing else than the stress times the area. The area is given, that was 200 millimeter squared. So you basically multiply this by 200. So you get here the stresses, this becomes, so if you calculate this, the forces, this will become 2,400 Newton. This will be, of course, 1,600 Newton, and this is 800 Newton. And then we get negative 800, negative 16. Yeah, that's 1 0. I was saying I'm missing one. This is negative 800, negative 16, and needs to be symmetric, and negative 2,400. So, and this is basically, you're almost done. Okay. So let me see where's the best way to draw it. I think on this side. Now let's look at the section that's basically missing. And that will be this section that we're going to take out, and we're just going to look at those forces acting on it. So if you now look at it, so here we have 5, 5, 6, 6, 6, 6, 5, 5. And then what we'll see is we had how many forces? 1,600 on that side. So this will be it. And what we can do is then split it up and just calculate how much the force is in this boom by just looking at, say, if this is going like this, it means that this is going like this, and this one is going like this. So we can take an equilibrium of these two. So we know we have this, we have 5, 5, 6, 6, and there must be a force that's in equilibrium. If we do, this is 800, so we get basically force equilibrium in x. That means 800 times 5 minus, well, let's do 800 times 6 minus 800 times 5. So basically is, what is this, 800? Because you get 800. So there's still a force going of 800 in this direction. So we get, let me see. So correct what I'm saying. This is 400. That was 400, right? Yeah. Yeah, so we get basically a total force of 800 in these two booms. So now we basically, because we have two booms, so the total force 800, because it's all symmetric, we can assume that's 400, 400 on each side. And this way, it will be the opposite. And here they will be in equilibrium. So that would be the full answer to the question. So it was just an equation of equilibrium of open shear flow, regular stresses using the moment, and only difficulty came from here. I think how the points were based. I think, what did I do again? Just for the equations, you get 1 point. Execution, you get 1 point, and this step you get 2 points. So they'll give you basically 1, 2 points here, 3. All the forces is 4, and this would be 6 points in total.
So part A was asking for what you did with there, and
Yeah.
part B is where you did the sum of forces.
Yeah.
I think part C was asking for the correction.
So, okay, yeah, part C. I skipped that part out of it. So the idea is, because when I did the grading, actually, I'd skipped that part, so I didn't have the grading for that. So I didn't take C into account. But part C, what you then do is, now you know to get this 0, you have to apply a negative force. And then you do again a similar thing. Well, now you're looking at, because this is double symmetric, you can look at 1/4. So you have basically these two panels. This is the tree. Where normally it was located 3, but now it's an unknown force of X, right? And this is, so you know with the shear flow here is 5, because this panel, you know the force 400 in this panel, in this case then draw it properly, is 400 this way. So what you do again is in equilibrium forces. So you know this panel is 5, this panel is 6. Let me see that correctly. That's 5 and 6. Sorry, no, Q1 and Q2, I mentioned it here. So this is, say, Q1, Q2. Let me see. So here, you know, we have 5. Here you have 5 as well. Here you have 6, because that's basically this boundary here, right? You copy that. And then, let me see, you just do equilibrium forces in X. So there's a shear flow here. Yeah, you do equilibrium forces in X, and then equilibrium forces in Y direction.
Okay. That makes sense.
Yeah. So it's again force equilibrium, and that will be C. I think I had C originally in it. I think I decided to skip that part, but it was not deleted from the question, so I didn't take that into account. But this would basically what these two parts you got graded on. And that's the thing, like you can often use simple tricks like equilibrium forces and open shear flow, and that will do the trick. Any questions on this? So, and a similar thing was true for question 1 actually. It was, you could have solved it significantly easier than most of you did.
Yeah, we did that area rule that Maxim did in the book.
No, even easier.
Yeah.
So let's draw that figure as well. So it was similar to the exam problem, or one of the problems we did in the class, or at least it's same geometry, different numbers. So you were given this, right? S, and what we're given is 5.4. 5.4. Let me see this correctly. Yeah, 12.17, 12.7. This is 17. And what did we have more? 37.9, and then 2 unknowns. And then we had, let me see the numbering. Okay, 1, 2, 3, 4, 5, 6, 7, we had Q1, 2, Q3, 4. So what most of you did, where they said, well, okay, closed section, so they made a cut here, they calculate the open shear flows. They find out, like, if you have made a cut in this 5.4, so this must be a correction shear flow, so you add it up and you got your Qs. Totally fine. But you can do it significantly easier. So what do we notice from this problem? First of all, we know it's symmetric, right? So it's symmetric. So what we know is, if we do an equilibrium of forces in X and Y, it's equal to 0, and equilibrium of forces in Y is equal to 0. So what do we get? So all the equilibrium forces in the Y direction, they must be equal to 0. In the X direction, sorry. In the Y directions, they must be equal to actually S. So S is equal to the component, the vertical component of 3, 4, multiplied by the vertical component of 3, 4. 2, 3, multiplied by the vertical component of 2, 3. 1, 2, multiplied by y 1, 2. With y 1, 2, I mean the vertical component of 1, 2, okay? So in here, negative minus Q 7, 8, which is 12.7, multiplied by y 7, 8. And this is multiplied by y 6, 5. So if you do the x direction, then you get the horizontal component of 3, 4, multiplied by this, multiplied by that. And because it's symmetric, you will see that the vertical component of xy, the horizontal component of 5, 6 is equal to this. Because these two are, this one is basically positive, this will be negative. Let me see. So yeah, we can use that to solve 1, 2, or we can use the vertical. Either one is fine. By the end of the day, it's nothing more than an equilibrium of forces. So what we can do is, let's use the equilibrium of forces in the y direction. So we ignore x for now, and we say it must be equal to s. So what we get is, let's do it here. So we know S is equal to 37.9 times 100 plus 17 times 60. And then we get, let me see, we have these two, because this will have a vertical component and this will have a vertical component. Am I trying to? Okay, I thought I did something wrong. This one is this way. That one is that way. Okay, good. Both of them have the same vertical component. Both of them are positive, okay? So that means 12.7 multiplied by only the vertical component between points 8 and 7, that's 70. And because you have the same here, we can multiply by 2 plus the vertical component of Q12, which is the difference in y direction of 1, 2, and that's 50. And because this is pointing upward, this one is pointing upwards, so that can be multiplied by 2 as well. S is given as 10 kilonewton, so we have 10,000. So you have one equation, one unknown. So in this case, Q12 is equal to 34.1 Newton millimeter. I noticed, and I had the solution, I did this. If you did a cutout for some reason, and I haven't checked it, I just assumed there was something I did maybe wrong or you guys did wrong, but I didn't subtract any points. A lot of you got 34.4 if I'm correct. I don't know why. And I did not subtract any points. It can be probably because how the numbers are obtained. Maybe this number is not exactly 5.4 if you would do the full shear flow correction or blah blah. I don't know, but I did not subtract any points.
Yeah, I think I got 34.3, but it's because after this, you get these corrections here for you do the negative SY over,
Yeah.
and that probably got rounded off.
Yeah, so probably that's why I assumed rounding errors, but I did not subtract any points. And because of if this was 34, I think it was 0.4, 0.3, most of you had one or two. I did not subtract any points. The B question was also slightly off, and I also did not subtract any points for that. But yeah, so the next problem, the next question was, okay, what if we move S to here? Right? What happens? So what you can do is you can say, well, everything remains the same. I determine my shear center, and what I do is I place S in the shear center and I add a torsion to it. And you could basically, again, you would have one equation, one unknown, and you could resolve it. What you would see is that the direction of 1, 2 remain the same. So in both cases, let's call this positive. So 1, 2 is Q, 3, 4 would remain the same for A and B. So both of times they would go into these directions, from 1 to 2 and from 3 to 4. I think that was part C of the problem. You had to basically just showcase this or specifically mention it. You got 1 point for it as well. And then if you calculate correctly, if you did the torsion part, I think you would get also one equation, one unknown, and the answer was, in this case, for B. So for A was 34.1, and for B it was 21.7. And C was noting that Q12 is Q34 is both positive. And I saw like multiple people use the cutout method, which is fine. I think it's because of because you guys got 34.3, something like this. This was off, but as long as you had 21 points something, you got full marks of it. So again, it seemed like a difficult problem, and theory was actually quite straightforward as well. Let's see. There's a quickly question, other two questions, and I'll go just in explaining what you could do for this one. Again, they were not very difficult. I think we did a similar question in class actually, or it's in lecture slides. You have a TIG weld, and you had another TIG weld, and they were both A's, so the dimension was the same, and you were given a moment and an alpha angle, right? So, the idea was behind this question, you set up your moment equation. So, let's see, I know that's y. So this one is ixx, iyy, minus ixy squared x plus so it means that this must be iyy, this must be ixy. I'm doing this by heart, so this must be ixx, this is ixy, and this is mx, this is my, and this is my, and this is mx. I'm correct. Okay. So you were given one m. So the question which you had to do is, first of all, find the moment of inertia. So for the square, you can say ixy is equal to iyy. So you have to find only one for the square. IXY is equal to 0 because you have symmetry here again, and you have IXX of the I-beam, and then it's different from the IYY because it's not doubly symmetric. And then you just have to use the Thickwald assumptions. So that means that you do 1 over 12. So in this case, if this is the height, so it will be height minus 2t to the power of 3 multiplied by the thickness. This is 2 times because you have 2, and then you do the Steiner terms. Oh, in this case, you don't have to do Steiner because y is less than 0. So plus in the top, that will be 1 over 12. And then you do b, this is total b, to the power of 3. No, yeah, b times t to the power of 3 plus AD term, so there's bt multiplied by h minus 2t over 2. Let me see, this here. So that's this part plus t over 2. So it becomes h minus t over 2 squared. And then you could simplify it or not. But the idea was you just did that, you did that for IXX, IYY. And then you notice that the moment, depending on alpha, what alpha is, you get moment mx is, what is that? M multiplied by cosine alpha, and my is sine alpha. And then of course, if alpha is 0, you only have mx. If alpha is 90, you only have my. And if alpha is 45, you have both. So then the y then x distance, because this was a if I'm correct, and this is totally a as well. So x and y would be a over 2, and y would be a over 2. And that would basically be your final answer. You could plug it in, and you can check if at 45 degrees, one of these two needs to be negative as well. So it was quite straightforward. Actually, looking backwards, this was worth most points because you had to do most steps in it. And because it was simple, most people got also full points on it. So regarding that. And there was nothing else to it. I think at the end was like explain differences within Thickwald, Thingwald. You could go multiple ways. You could say, as long as you came in something in the direction of like, well, okay, for Thickwald the stress will be lower because you have a high moment of inertia, that will get you full marks. It was also one just 1 mark. You could indicate that you were basically neglecting T's, therefore reducing again moment of inertia, and everybody got, I think, full marks on it unless you just forgot to answer that question. And that's a lot of people did actually. If you lost points in this question was in the final step, a lot of people just forgot to answer C. And it was simple as just saying, well, the moment of inertia changes in your disadvantage of the I-beam. Or if you go Thingwald, your moment of inertia reduces. As simple as that. You didn't have to do any complicated solutions. Some people actually went in, filled in numbers, and showcased the difference. You didn't have to go that far. Any questions? Okay. And then we had our last problem. And that was again, be careful on the what I'm asking for, because I think, let me see, it was something like this, right? Should have brought it down. Something like this, I think.
Yeah, some numbers.
Yeah, so it doesn't matter. All the boom areas were A, so everything was A, 0.1 inch squared. and you were given a moment, right?
Mhm.
Yeah, and a moment, like I said. Okay. And you were asked to calculate the load, and load was specifically ordered. So that means again, you use your stress equation, m times y over ixx, and you multiply this, multiply by the area to get the force, the load in the sections. So what you have to do for this, you have to find the centroid. You know it's symmetrical on one axis, so you do know that. I think this was 5, 5.
I think the bottom's all flat except the center part where it
Yeah. That's true. It was not double symmetric. You're right. I think it was something like this
Yeah.
actually. Because I know it was 15 apart. So this is 5, 5, and 5. So this is 5, and then we have here 1 as well. Doesn't matter. So you know that x bar is in the middle. So that was from this point of view. If this was our origin, 0, 0, it would be 15, and then y bar would be 4.33 from the distance, and I will put it just above the center. So you have to calculate the centroid first. Using the centroid, you could calculate, well, moment of inertia was just simple. You could just do by squared, right? And this, of course, by squared is now needed. This y squared has you have to fill in the right y distance. And then you could plug in to get the stresses, and from stresses you could multiply with area to get loads. So what most people did wrong, well, let me say first of all, when you calculate your moment of inertia, your centroid, clearly state where you're taking that centroid from. So with the most of the time I had to figure out, because some people got like 7 and then or 8 number, and then for me it was hard to figure out where people start off at. Some start at this point, which is fine. Then you get just a negative number. That's fine. Some start from here, so they got instead of 4, they got I think 6.33. So it took me a while to figure out where you started from. So you can avoid confusion and help yourself by just saying, taking a centroid from point, I think this was A and this was L, point A, point 1, point 3, doesn't matter. But as long as you state clearly in it. A lot of people also started from the middle, which is fine. Then you get 1.33, but it took me a while to figure out, okay, that's the location where you started from. So some people forgot the y distance. So I think this was worth 2 points or 3 points, I remember correctly. But which I would do is, if you got wrong y, I'll subtract 2 points for it, and the rest you will get full points given out even though you got incorrect solutions. And this was at the end worth also, I think, 1 point or 2 points. So a lot of people missed these 2 points because they just did not answer the question. It was asking for the loads, was not asking for the stresses. So you have to multiply with area. Other than that, it was a very straightforward problem, I think. So the exam was, I don't think it was very hard. I think it was easy, to be honest. I think the only question that required a bit more insight and intuition was question 4. But 1, 2, and 3, I did think they were pretty straightforward. Like I said, for shear flow problems, like the one that we had, you could just solve it by doing a force equilibrium if you're getting shear flows. It simplifies your life. Making the cut, doing everything, also fine. Should get the same answer. Majority of did get the same answer. Let me see. I think for the next exam will be again, I made it yesterday, will be posted again Sunday morning 9 a.m. due Tuesday morning 9 a.m. It's similar to this one, it's 4 questions. Yeah, it should not be any harder or easier than this one. I think it's comparable in difficulties. And then, yeah, I will do the same thing. I'll grade it, and then post the solutions online, like the grades online. And what I will do is, if anybody has objections against it, they can reply to me or email me until Friday, because Friday will be the deadline for me to post the grades to mysc.edu. And once I'm there, it's very hard and very painstaking to change it, because I have to sign forms, blah blah. I don't want to do that. So if you disagree with your grade, if you want to look into it and come and discuss what you did wrong, what you did right, and where you lost points, come to me before Friday next week after the second exam. Other things, yeah, and yeah, eventually you will get a letter grade, so you will not get an on your salaries. Or mysc.edu will just give you the letter grade. And a lot of people, I noticed as well, they will get, like, say, your final grade would be 7.9 or 8 point, say for example 8.39. So all these things I just round up to a 9, so that will give you an A. And I did the same for the other grade as well. So if you were like that, I think the lowest grade was a C, which was a 7.34. So because this one got upgraded, this one got upgraded to a 7.5, which would be a C plus, based on this grading scheme that's in the syllabus. I think majority of the people, I think there were 4 A's, a lot of B pluses, a couple of B's, and 1 or 2 C pluses, if I'm correct. So I think everybody that handed something in did pass, and there were like 4 people who did not hand in anything. And I think 2 of them are even withdrew from the course, so, but it's still on my list. But yeah, so if you have any questions regarding any topic, contact me. Again, Sunday I'll be slow on replying, so if you have questions about the second exam, don't expect a quick reply from me on Sunday. On Monday I will be back in the office, so that will be fine. I'll try to answer still on Sunday, but it might take a bit longer. Other than that, same procedure, 48 hours, do the exam, make a scan version, send it to me. Please double check your exams as well. So, okay. If there's no questions, then we can call it a day.